Hello everyone, welcome back to the channel PHYSICSSIRJEE. Today we meet again in the much awaited resolved series, right, with another resolved challenge. Okay, so here we are having a problem from Irodov, right, and we are not going to just look at the solution to the problem. We are going to look at one of the sentences written in the question by Mr. Irodov in order to actually understand the deeper nuances of the concept of viscosity. So I have picked up the question 1.333 from the problems in general physics in Irodov, and you could see that it talks about a rotation viscometer. Viscometer is a device which is used in general in order to find the coefficient of viscosity of a particular liquid. So as you could see in the left of the screen, that is the usual diagram of a rotation viscometer, in which you actually have a cylinder and coaxially surrounded by another cylindrical shell, in which in between the two the liquid actually is dropped, and after that they'll be given some different angular velocities. The inner cylinder and outer cylinder are usually rotated at two different angular velocities, and over a period of time the viscous liquid inside would achieve a steady state. Okay, so by studying that steady state you would be able to estimate the coefficient of viscosity. So this is the basic introduction to the viscometer. So the issue that I am going to address in this problem is not just the solution of this question, that actually would become trivial, but the formula that Irodov asks us to consider solving this particular problem. So I've zoomed that, so you could see that he's talking about the stress on each of these cylindrical layers, right, which is very important for viscosity equation, right? That stress, he writes it as eta into, this is a surprise, r into dou omega by dou r. Whereas usual discussions under topic of viscosity talk about velocity gradient, here he is asking us to take the angular velocity gradient. So the first issue that we are going to resolve in this problem before solving it would be to try to understand why does Irodov sir write angular velocity gradient instead of the usual famous velocity gradient. So is he assuming something only for this problem, or is this equation correct actually in the rotation viscometer? Okay, so this is the idea we are going to explore now. So first we'll try to do the basic understanding of viscosity and coefficient of viscosity definition from actually NCERT. So these pages have been picked up from NCERT, so that even a student who is preparing for JEE exams will be able to understand the basic meaning or a definition of viscosity. So these are beautiful diagrams given, and I wish you people actually should have read through these pages of viscosity from NCERT. Okay, so I'll just go through or skim through these things very quickly for you. So what he talks about is for any layer of liquid, so I'm pointing out the lines that I'm reading here, its upper layer pulls it forward while lower layer pulls it backward. So he's talking about a layer which is translating in the rightward direction. Okay, and in a viscous fluid what actually happens is each of these layers will not move with the same velocity. So AD, which is on the floor, is almost fixed, and the topmost layer moves the fastest, because of which the layer which was supposed to be this ABCD over a period of dt seconds actually gets sheared, or sheared means it should change its shape, as you could see, by an angle d theta. Okay, so all this you can read, and then he talks about, unlike a solid, this is the most important point, unlike a solid, here the stress is found experimentally to depend on rate of change of strain and not strain itself. Okay, so remember, if any solid of this kind is applied a shearing force on the top, we talk about in the modulus of elasticity topic of Hooke's law, the shear stress is proportional to shear strain. That is what we talk in solids. Whereas in liquids, and here means these are Newtonian fluids or Newtonian liquids. So in Newtonian fluids, experimental law talks about the stress not proportional to strain, but rate of change of strain. Okay, so rate of change of strain is nothing but this angle rotated in dt seconds divided by dt, that is nothing but d theta by dt. So it's a pretty simple calculation. You wait for this dt seconds to go over, then the speed of this particle would have taken this to point E, whereas this stays where it is. So this is your vdt. Okay, and this is small angle, right? So you can consider it as tan of d theta. Okay, so that would be this divided by this. So that's what I've written here. v dt divided by L, and rate of change of strain comes out to be velocity gradient, which is v divided by L. So for this diagram, rate of change of strain comes out to be velocity gradient, and therefore we define the coefficient of viscosity using this final formula in which the velocity gradient appears. Doesn't mean it is basically defined on the basis of velocity gradient. Velocity gradient comes as a after effect of taking rate of change of strain. So this is a basic important thing that is given even in NCERT, that you need to understand that coefficient of viscosity is related to the rate of change of strain, or simply stress is proportional to rate of change of strain is the law of viscosity for Newtonian fluids. So we'll take this basic law and apply it to the rotation viscometer, and whatever it throws up we have to accept, whether it is velocity gradient or angular velocity gradient. Let's move forward. So we'll try to apply the definition that we learned in the NCERT textbook to the viscometer. Okay, I've drawn the top view of that viscometer. Okay, right. Ignore these omegas. So these omegas I have developed for the future challenge, so forget about it. After this particular resolved series, I'll post a challenge for application as usual. Okay, so in the Irodov challenge, what they have done is they have given the inner cylinder 0 angular velocity and outer cylinder an angular velocity of omega 2. Okay, so right, only in the inner fluid that you're talking about, imagine I take a small chunk of that fluid. The chunk is here. You can see that this particular part, I don't want to shade it, right? So this particular part, which is at a distance small r and a width of dr. Okay, so I have transferred that here for a better visualization. Can you see that chunk, trapezoidal chunk that I have here? Okay, now imagine there was no gradient of angular velocity. Imagine there was no gradient of angular velocity. What does that mean? If this point A's angular velocity about center is omega, then point B's angular velocity is also going to be omega. So A's speed would be r omega because A is at a distance of small r, and B's speed would be r plus dr into omega because you know it is at a greater distance. But you see I have written same omega. Now I argue that if this situation happens, even though there is a velocity gradient, I would say the shear would be 0. When gradient of omega is not there, I will argue that the shear here would be 0. Reason is very simple. Here in the next dt seconds, the white line, this is the white line, that white line is the line that connects A to the center, that is r in radius. This is an exaggerated figure. This is r and this is dr. So the white line, which is r, rotates by the same angle as the red line. That's the whole idea, right? When you have all of these obeying the same omega rule, this entire stick kind of thing will rotate by the same angle. So there won't be any twist or any shear in the line AB. Okay, so that's and I have shown that in this particular figure. Imagine I wait for dt seconds, this solid red line becomes this dotted red line. Can you see? Every point on this particular line now has become this one. So you could say that the trapezoidal shape would be maintained. That maintenance of shape means there is no shear that has happened to that. So without velocity gradient, even though there is a without angular velocity gradient, even though there is a velocity gradient, shear won't happen. Okay, so no rate of strain produced. The strain rate is not there because there is no d theta. The angle, you might argue there is a rotation. Remember, rotation should be with respect to the bottommost point of the topmost point. That is not happening. The same orientation would be there. So I can almost say that if there is an observer sitting at point A, he would see that there is no relative velocity for point B. Relative velocity of point B with respect to A is 0. Don't just subtract these two. So you need to know how to use relative velocity in a rotating frame. So for that, I've already made a resolved video. So I'll leave the link in description there. So it's not just VA minus VB. So if someone sits here and watches this B, he would say that there is a 0 velocity. So he'll not see any twist in this angle. So with that explanation, let's move forward. Now with the gradient there, right? So if gradient was available for the angular velocity, right? So then this AB line, if I have redrawn here, if this has moving with r omega velocity, then this point would be moving with r plus dr. Instead of omega, now I have an omega plus d omega. That is what the gradient means, right? You will have a different angular velocity as you move different distances. Because of this, if someone sits here, imagine I've drawn only this line, so I've replicated here, and imagine I'm having an observer who is fixed to the rotating frame of this point A. So this observer would now see an angular relative velocity to this particular point, okay? And that is due to that extra term that you had. If this d omega was not there, then you would not have any relative velocity for this, which I argued already. You don't use VA minus VB just like that, okay? So which means, as seen by this point, now this line will not rotate by the same angle as this line, okay? So this will get a small twist because this fellow sees some really linear velocity for this, okay? And you give it a dt second. So from here to here, I've changed the frame, and from here to here, I wait for dt seconds. So after dt seconds, you could say this point just moves this way with the relative velocity multiplied by dt. And this angle is called the change in that particular angle, or this will cause the rate of strain that we are looking forward to. Okay, so simple, again, simple triangle, angle is equal to opposite by adjacent, which I wrote here, right? You could see that. And therefore d theta by dt, which we require as the strain, now simply spits out r into d omega by dr. Okay, right? So you recognize solids stress is proportional to strain, which obey Hooke's law obviously, and Newtonian viscous fluids where stress is proportional to strain rate, this stress should be proportional to strain rate, and that proportionality constant is defined as eta. Okay, so eta into d theta by dt, r d omega by dr. So what Irodov sir wrote is perfectly all right. Maybe he was very kind enough that this entire derivation need not be done and students can easily apply this directly, but now we have learned how this actually is derivable and can be used even in the future topics. And please understand, this is well within JEE syllabus, and it is based on, as I have proved, on the concept that is written down in NCRT. So you need to remember this strain rate definition. Okay, so let's move on. This is the formal one. My whole focus was not solving the problem, but I thought there should be some closure to the resolved thing. So that's why I wrote the actual Irodov problem. In actual Irodov problem, remember, the inner cylinder was at rest, outer cylinder was moving at omega 2. That's what he has given. So this is, let's say, a differential layer element, cylindrical layer element of inner length L, and this is R and R plus dr. Okay. Now in steady state, if this one should not change its speed, whatever torque gets applied on it on the inner surface, the same torque in anti-clockwise direction should be applied in the outer surface. So these two torques cancel each other, and net torque on this should be 0. There should not be tau plus d tau. That's a steady state. So we already know from the previous derivation that sigma is eta r d omega by dr, right? So when you write torque here, which is nothing but force into perpendicular distance, so force into r, and the value of force is the stress multiplied by area on which stress is acting. You could see the curved surface area, which I can't show in this figure, but inner surface, you can visualize that it is a cylindrical area of 2 pi r into L. So 2 pi r L into sigma gives you force, force into r is the torque. That I am saying is C, every layer that I go, I should get the same torque. Okay, so I'm writing it as C, which is independent of R. Okay, right. So there were two questions. He asked us omega as a function of R, which we'll try. And also he asked what is a torque produced, moment of force he asked, which is torque. So we have to solve for C, right? And also we have to solve for omega versus R relation. So I just rearrange this. Eta I'll substitute here in terms of sigma, and then rearrange this. I'll get d omega by dr from here is equal to C divided by this entire thing. Now this is some one mathematics which I also like, which should enlighten the students equally, is my job is to find omega as function of R, and my job is also to find C. Remember, C is also an unknown quantity. So here is where I'll try to use two types of integrals, okay, using boundary conditions. So one integration I'll do by taking obviously dr on that side is from the inner cylinder to the arbitrary point, any arbitrary point where the distance is smaller. So inner cylinder distance for radius is r1, arbitrary distance is r, and that corresponding omega that I don't know is omega. So this is one integral. Second integral, I'll do it completely, right? This is like a thing that is done from inner to outer completely. So inner cylinder R1, omega is 0, outer cylinder R2, omega 2 as directly substituted. So if these two integrals are performed, then this outer term is common. I'll divide the two equations. So once I divide the two equations, that's the beauty of this method. what actually happens, as you could see here, is that c by 2 pi eta L gets cancelled, and omega minus 0 divided by omega 2, I've taken it that side, is simply the ratio of these two expressions. So you nicely get the actual relation. Okay, right? So that's the final answer for omega versus r. But from here itself, if you have actually performed the integration, completed it as omega 2, remember omega 2 is a known one, you would also get the value of c. What is c? C was nothing but the torque, which was the second question. Okay, so even though the idea was not to solve the Irodov question, but we have learned more than solving that question, which was understanding how friction actually acts in a rotation viscometer. So it's velocity gradient only in the linear type of flow like this. It's not a general definition. General definition is rate of change of strain related. Okay, so I hope you understood a lot from this particular video, both in terms of concept and also the Irodov solution. And I would like you to stay tuned, because I'm going to make a application problem, as is the case with any resolved series. So this is already the 7th video. So if you want to see other resolved questions, please go to the playlist. I have made a separate playlist of resolved, and also ensure that you stay tuned for the concept application problem for this particular. I'll make a problem on rotation viscometer and post it very soon within coming few days. Okay, so please do like, share, and subscribe to my channel, and stay tuned. Hit the notification bell icon so that you get your regular updates. Okay, we are going to come up with many more updates as the JEE mains and JEE mains, NEET, and JEE advanced exams are closing by. Okay, so thank you, and see you in the next video.